T-minus 15 seconds. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Main engine start, 0, and liftoff of the Atlas V with Curiosity, seeking clues to the planetary puzzle about life on Mars.
The program is in right on time. 180 operating at 100% thrust as expected. And throttling down to 76%. Program complete. And NSL is now breaking the sound barrier. SRB chamber temperatures following the nominal curve. Everything will. And we pass through max Q. We're on closed loop on Atlas VU. Signatures as expected. SRB profile continues to look nominal, throttling back up to 100% thrust on the RD-180. Engine parameters looking good. Flight control disturbances look as expected. SRB pressures running right as expected. Coming up on SRB burnout, we have burnout of the SRBs. Everything is looking good. 10 seconds to SRB jet. And we have first pair and second pair. Both sets of SRBs have successfully jettisoned the vehicle. We've re-enabled guidance. Everything is looking good.
Stephen Hawking once said, "The long-term survival of the human race is at risk as long as it is confined to a single planet." My name is Tom Rooney. Like many Americans, I was inspired by the landing of Curiosity on Mars. I started to ask, why should we have a space program in the first place? I believe there are many valid answers to that question, but perhaps the most compelling is the fact that our solar system is a very dangerous place, and we ought to be able to defend ourselves.
30th of June 1908, 7:14 a.m. local time, Siberia. The region of Tunguska sees the biggest explosion in human history. In 1 hour, the explosion and the great fire that followed destroy a region of forest the size of Greater London.
People who observed that thought the end of the world had come, Judgment Day, divine intervention.
They say that the Tunguska explosion had the force of more than 1,000 Hiroshimas. Millions of pine trees, larches and birches are destroyed by the pressure wave and the fires. A shockwave circles the world, leaving its mark on seismographs everywhere. But no one can understand where it has come from. It is 20 years before Soviet scientists discover the true scale of the disaster and record it on film.
One reason it took so long for scientists to reach the site is that Tunguska is very remote. From above, you can see a circular feature at the site, but that's actually not an impact crater. This led some to believe that an asteroid was not the actual cause. Theories included everything from a natural gas explosion to an alien weapon. However, new scientific data gained from the observation of an asteroid hitting Jupiter in 2009 has solved the mystery.
The Tunguska disaster had baffled scientists for almost a century because no impact crater or meteorite has been found, and many of the trees in the area were flattened but not incinerated. Many scientists finally came to the conclusion that a space rock exploded as an airburst when it hit our atmosphere.
So this was an atmospheric explosion. It was really the only one we knew about, which made it seem unusual, very much like the Jupiter impact, and that in fact these are probably more common than we had really thought.
The asteroid was originally calculated to be 200 feet in diameter and released 10 to 15 megatons of energy based on the devastation in the area. But Boslow now thinks the size was much smaller.
When I did the simulation with a 15 megaton impactor, the fireball, the very hot gas that emerged from the explosion, descended all the way to the surface. That would have incinerated all the trees and created this zone of complete devastation that was not observed at Tunguska. The trees were not incinerated. Therefore, the mass would have had to have been less than people had previously thought.
Boslow designed new simulations to show that the momentum effect of the air blast, not the size of the rock, caused the devastation.
I modeled this as an object coming in at a 35-degree angle, and I exploded it when it descended below about 7 or 8 miles above the surface. It comes in, explodes, but the jet of hot material continues to descend. So what you see is the momentum effect after the explosion. The momentum is the velocity that continues to carry the mass downward before it finally slows down and stops.
Boslow's new simulations also account for the fact that the terrain was not flat, so the winds from the blast were amplified by the ridge lines.
But the gust is stronger on the top of the ridge and just beyond the top of the ridge. That's where you would tend to have the most trees and the most damage.
Boslow's new research may mean that finding smaller asteroids is more important than previously thought.
One of the conclusions that results from this work is that smaller asteroids can create significant damage at the surface.
Regardless of the size of the asteroid that hit Tunguska, it leveled 500,000 acres of forest, over 830 square miles. If we take a city like Springfield, Missouri, for example, the third largest in the state, the blast radius would have easily engulfed all of it. So how many asteroids are out there? How big are they? How many could hit Earth? These questions have been answered in part by the launching of a very special telescope in 2009.
WISE is the Wide Field Infrared Survey Explorer. WISE is going to find hundreds of millions of objects spread over the entire sky. And for us, that's like a treasure map. We think there are about as many grains of sand on this beach as there are stars in the entire universe. So the task of finding rare objects in the universe that we're interested in requires the maps that WISE is going to make. It's a bit like using this metal detector here to try to find gold coins that are buried in all of this sand. WISE consists of a fairly modest-sized telescope, about 40 centimeters in diameter, that would sort of fit under your arm. WISE is going to survey the entire sky in 4 infrared wavelengths over 6 months. All-sky surveys are one of the basic tools that astronomers use to find interesting and unusual objects. It's sort of like the GPS of astronomy. One of the most exciting things that you expect to find with an all-sky survey like WISE is the unexpected. We expect surprises, things that we have no idea about today. One of the projects WISE is going to be doing is studying the population of near-Earth objects. These are asteroids and comets whose orbits get close to Earth's orbit. Now, this doesn't necessarily mean that they're going to hit the Earth, but we do want to pay some attention to them. With WISE, we'll be able to tell something about how many there are, what their sizes are, and what they're made out of. Whether they're soft and crumbly like this ball of sand or solid rock like this rock right here. In visible light, an object that's small and shiny reflects the same amount of sunlight as an asteroid that's big and dark. But when we look with an infrared telescope, we're seeing heat that's emitted from more sides of the asteroid, so we get a much better true measurement of the object's size. And this is important because it allows us to tell whether or not we're dealing with an object that's this big or an object that's this big.
With data gathered by WISE, NASA was able to give us a better idea of what's out there with this near-Earth asteroid census. Each symbol represents 100 objects. For example, at the top, we can see there are just under 1,000 near-Earth asteroids that are over 3,000 feet across. We know about 900 of them. However, at the bottom, we can only question how many near-Earth asteroids are under 300 feet across. Remember that the Tunguska asteroid was originally believed to be around 200 feet across and is now believed to have been much smaller. Most of these asteroids pose no danger, but some of them are potentially hazardous. The green circle here represents the orbit of Earth, and the blue circle represents a typical near-Earth asteroid. We can see that a typical near-Earth asteroid crosses the orbit of Mars twice in its journey around the Sun. If we were living on Mars, these would be potentially hazardous. The red circle represents our own potentially hazardous asteroids. This map of Mars shows how it has been continually battered. Scientists have counted over 635,000 impact craters on Mars. The blue area near the bottom is an impact crater over 1,400 miles across. Our nearest celestial neighbor has also been hit repeatedly. Because our Earth has a significant atmosphere, water, dynamic weather, and erosion, impact craters are not nearly as evident, but they are there nonetheless. Here's one in Australia. Here's one in Namibia. Here's one in Chad. Here's one in Ghana. Here's one in Canada. Here's one in South Africa that's 190 miles across. That's over 2% of the diameter of the Earth. Here's one in Arizona that's a mere 4,000 feet across and 570 feet deep. It's much smaller than many, but if you stand at the edge of it, you will be very impressed. Many impact craters are virtually invisible. Chesapeake Bay, for example, was formed in part by an impact crater 53 miles across. Special 3D imaging makes it visible. This map shows the locations of known impact craters. Dense concentrations like those shown in Europe are probably typical. Probably the most famous asteroid is the one that hit Mexico at the Yucatan Peninsula. Though it was a large asteroid, the impact crater is difficult to see. A closer look reveals the faint outline of the impact centered at the red dot. Special imaging that measures gravitational anomalies makes it clear. This one is 110 miles wide, and scientists believe it wiped out the dinosaurs.
The asteroid fragment's enormous mass is only part of the threat. The other part is velocity. But as it gets closer to the planet, the Earth's gravitational pull gets stronger, and the asteroid accelerates past 40 to 45,000 miles per hour. And mass times acceleration equals force. As the asteroid encounters atmosphere, friction turns it into a fireball, swooping over the Atlantic and aimed at Mexico. and the Alamosaurus. It takes just 4 minutes to cross the ocean. It crushes and superheats the air surrounding it, transforming gas and debris into white-hot plasma. At 35,000 degrees, it's burning brighter than 1,000,000 suns.
This graph shows what are known as extinction events. To the right, we see the Cretaceous Paleogene, also known as the KT extinction 65 million years ago. That's the one that killed the dinosaurs. In human terms, that's obviously a very long time ago, but in geologic time, it was relatively recent. Specifically, the graph shows the percentage of marine species that went extinct over time. The KT extinction not only killed the dinosaurs, but it killed about 1/2 of all marine species. The Permo-Triassic extinction in the middle killed far more. On one hand, it might be easy to ignore the actual danger of a large asteroid strike because they happen infrequently in human terms. In geologic time, they happen frequently. Today, near misses are thought to occur about once every 2 or 3 years. Most go undetected. In 1989, for example, an asteroid 1,000 feet across would have hit if it had arrived only 6 hours earlier. It was detected 9 days after it passed. It was named Asclepius. Its impact would have created a 600 megaton blast. The atomic bomb on Hiroshima at the end of World War II was about 15 kilotons. It leveled everything for a mile. 1,000 kilotons equals 1 megaton. The Tunguska asteroid was probably about 120 feet across, and its explosion was around 10 to 15 megatons. That's 1,000 times Hiroshima. Asclepius, at 1,000 feet and 600 megatons, would have been 40,000 times Hiroshima. On November 11, 2011, an asteroid discovered only 6 years earlier, hence the name 2005 YU-55, also came close to hitting Earth. It was 1,300 feet across. Looking again at the near-Earth asteroid census, we see that such asteroids are actually only medium-sized. Even the small ones, like Tunguska, at 120 feet, can be devastating. Scientists estimate that we have detected only 20 to 30% of potentially hazardous asteroids. It should also be noted that comets pose a similar danger, and most of them are also undetected. Among the potentially hazardous asteroids we know about, the most notable is 99942 Apophis. It's named after an ancient Egyptian god that swallows the sun and causes earthquakes. These images show how it appeared in the night sky. It's 885 feet wide. That's 8 times larger than the Tunguska asteroid, and it's headed towards Earth in 2029. NASA says Apophis will miss the Earth, though it will pass so close that it will go under communication satellites. They say gravity may pull it closer and give it a small chance to hit 7 years later. Critics contend that NASA scientists ignore certain details that allow for large uncertainties, and the chance may be much greater. Some Russian scientists believe an impact is imminent. This image shows the path of risk. Even if Apophis were to hit the ocean, the following tsunami would be enormous and devastating. Though it would be unlikely to cause an extinction event, we should all be aware of the long-term inevitability of a large asteroid impact.
Even though it is moving at over 720,000 kilometers an hour, that's almost 450,000 miles an hour, the asteroid appears eerily slow because of its size. The actual impact happens in the Pacific Ocean, just under 1,000 miles south of Japan. The crust of the Earth is peeled away like an orange skin by what is called the crest tsunami. Even the deepest part of the Pacific Ocean looks like a thin film. Huge chunks of debris the size of city blocks are hurled into the air. The entire Japanese archipelago is disintegrated, as is some of the Asian continent. The shattered remains are hurled out into space way beyond the atmosphere to bombard the Earth with deadly intent when they re-enter. At 7,000 meters, 23,000 feet, the rim of the crater is higher than many mountains on Earth today. The size of the crater would be a distance of 2,500 miles or 4,000 kilometers. And this is just the start.
When an asteroid hits the surface of the Earth, the material is heated up to temperatures that get up to the point of, say, 4,000 to 6,000 degrees centigrade. This is as hot as the surface of the sun. When an impact hits, it's not just the crater that forms, it's not just the area where the impact occurred. It's all the heating that's created in the atmosphere and around it. So heat really is the killer.
Moments after the impact, rock vapor, the temperature of the sun, begins to engulf the world. Could any life at all survive this impact? Immediately after the impact, the rock vapor rises up from the crater in a dome, then spreads out in all directions across the globe. 3 hours after the impact south of Japan, the expanding wall of vaporized rock reaches the mountains of the Himalayas. The perpetual snows are instantly evaporated. Soon the wall of fire reaches the Amazon, the furthest distance from the point of impact. The forest spontaneously combusts even before the rock vapor arrives. Just 1 day after the impact, the entire planet is covered. Every living plant or creature is vaporized. It's been estimated that this vapor would cover the entire globe for almost a year. It would be as if the sun had come to Earth. The the ocean would start to bubble and boil, and as the water evaporates, the oceans would drop at the rate of 5 centimeters or 2 inches every second. Even the salt deposited on the ocean floor vaporizes, and then the very bottom of the sea melts. Nothing is left untouched. One month after the impact, the surface of the world has been sterilized. The oceans have vanished. All that remains is the superheated bedrock. It is thought that an impact like this happened 6 times in the violent past of the Earth's history. If there was life, it was assumed that it too would have been wiped out, only to begin again.
Stopping a large asteroid from hitting the Earth is something human beings will inevitably have to do if they wish to continue as a species on planet Earth in the long term. This will require advances in technology, but more importantly, it will require the will to succeed. I believe our space program is the best conceivable path to success. Yet, if we look at the hard numbers of our dedication, we are failing. Our investment is small. Investment in the space program peaked in 1966 at less than 4.5% of the national budget of the United States. Then, it was drastically cut, even as men were walking on the moon. Though the space budget has remained relatively stable since the mid-1980s, it has continually shrunk as a percentage of the national budget. In 2012, it is less than 0.5%. The dinosaurs went extinct because they could not stop an asteroid. Maybe we can. It's an existential question. Nature has repeatedly rejected species that are unable to survive because they do not have the ability to survive. If we fail, we might be studied in the distant future by a new species that somehow evolves the ability and the will. They might look upon us as simple-minded fools for not trying hard enough.